Hello everyone, I am Mohammad Mudassir and this is my teammate Krishna Kumar. Today, we will be presenting on efficient and effective time series forecasting with spiking neural networks. Let's get started. Time series forecasting plays a critical role in various real world applications such as traffic prediction, energy consumption, and financial modeling. Traditional approaches, including statistical methods, CNNs, RNNs, and transformers, have shown promising results, but they often come with very high computational costs and may struggle to efficiently capture temporal dynamics. Spiking neural networks, inspired by the brain's neural mechanisms, offer a promising alternative due to their event driven nature and energy efficiency. However, effectively adapting SNNs for time series data remains a challenge, particularly when aligning time steps and preserving continuous temporal information. This work aims to bridge that gap by developing efficient and effective SNN based models tailored for time series forecasting, ensuring both high accuracy and low energy consumption.
Basic unit of this model is a spiking neuron. Unlike traditional artificial neural networks or ANNs, SNN will mimic the biological neurons in the human brain. So the key idea is a spike-based communication. And each neuron will be having a threshold. When the input value exceeds this threshold, the neuron will fire. Otherwise, it will remain inactive. So this makes the system event-driven and can be treated as binary. So now, if you look at the diagram that we have here, you will notice that there is a time component as well, right? So x-axis is the time. And since our goal is time series forecasting, at first glance, this seems like a perfect match, right? But is it really that simple? Let's find out. So just like we discussed, time series data is inherently sequential and it obviously requires some sort of temporal modeling. That fits well with the nature of SNNs, but there are a couple of challenges that we will be facing while modeling. The first issue is the encoding part itself. Time series data uses floating point numbers while SNN uses binary spikes. So the conversion can cause information loss and this might introduce noise as well. And the next thing is temporal alignment. Time series data is continuous, but SNN works with discrete spikes. So the data has to match, right? And it's very difficult to align the time steps properly as well. The next one is the model selection. There are no standardized guidelines for choosing the best SNN architecture. And since SNNs are in mainstream, the architecture selection is mostly empirical. Plus, each dataset and domain may require different tuning of parameters as well. So to tackle these challenges, they introduced a couple of mechanisms. For encoding issue, they used two types of encoding layers to convert the continuous time series data into the respective spikes. For the temporal alignment, instead of directly using the continuous data, they split it into multiple time intervals. And lastly, they have created CNN, RNN, and transformers counterparts of SNNs for time series forecasting. So in the next couple of slides, we will be explaining about the methodology. So over to you, Ali.
Now, let's jump into the methodology. Our approach consists of two key components: temporal alignment with spike encoders and spiking neural architectures. Temporal alignment is crucial for ensuring that spike-based representations effectively capture sequential dependencies. Inspired by prior works in image processing, we introduced an external dimension to facilitate spike information transport. Our key idea is to divide a time step delta t of time series into TS segments. This transformation converts a floating point representation with dimensions t into c into spikes with dimensions ts into t into c.
To effectively handle the time series data with SNNs, like we discussed, we need specialized spike encoders. These encoders should not only generate spikes but also retain the temporal information of the input. So in the past, especially for image processing and all, repeating the same input TS times has been a common approach. But this won't work here since it disrupts the continuity of the data. Instead, we will be going with spatial encoding techniques. The first one is delta-based spike encoder. So it captures change over time by computing the difference between two consecutive time steps. So xt minus 1 is the difference followed by a linear operation to adjust the scale of the difference. Bn stands for batch normalization and Sn is the spike neuron function. So this one is useful for capturing dynamic variations. And the second one is convolution-based spike encoder. So it applies convolutional transformation to extract meaningful spike representations. Here, convex stands for convolutional operation on X. And this extracts spatial and temporal patterns. So this will help to learn richer spike representations instead of relying purely on temporal differences. So regarding the architectures, the authors were able to design and develop SNN counterparts of a couple of mainstream models. So for TCN, which stands for Temporal Convolutional Network, there is Spike-TCN. For RNN, there is Spike-RNN. And for transformer, there is Spike-former. So in these architectures, they replace relay with leaky integrate and fired neurons because it will align better with spiking mechanisms. They use spike-wise, element-wise residual connection to preserve the gradient flow. And they were able to implement softmax-free spiking self-attention, which removes unnecessary floating point operations as well. In the result section, we'll be considering three things. First of all, the efficacy of the models in terms of the performance. And the second one is the time series prediction in capturing the temporal characteristics. And the third one is going to be the energy consumption. So they have used 4 datasets called Meteor, PEMS Bay, Solar, and Electricity for comparison. And they have used 2 evaluation metrics, root relative square error and the coefficient of determination. So we have all the details regarding the equations here, and these are the variables. So we have our result table here. So we'll be comparing different ANNs and the respective SNN counterparts. So here the best and second best results are in bold, and it is very evident that SNN models are comparable with some of the best traditional models out there. And under certain settings, Spike-former and Spike-RNN outperform some of the ANNs as well. And on top, we can see 6, 24, 48 and all, right? So those are the prediction lengths, or L. Let's talk about temporal analysis. To validate the capability of SNNs for time series prediction and in capturing the temporal characteristics, they actually conducted experiments on both low frequency and high frequency synthetic periodic signals. So we can see all 3 shows great performance in handling the time series data. And the one thing to note is that Spike-TCN is relatively weaker in high frequency scenarios. Energy reduction. Here the SNN models will be running on a 45 nanometer neuromorphic hardware, which has been specifically designed to imitate our neurons. So we will be comparing energy consumption per sample of ANNs and SNN counterparts. So OP, that is in the table, is in FLOPs for ANNs and SOP for SNNs. FLOP stands for floating point operations and SOP stands for synaptic operations. So we can see SNNs consumes significantly less energy than ANN counterparts with an average reduction of approximately 70%.
To summarize, our proposed spiking neural network based approaches have demonstrated strong efficacy in time series forecasting, achieving performance comparable to traditional methods across multiple benchmark datasets. One of the key advantages of SNNs is their energy efficiency. These models significantly reduce computational energy consumption while maintaining high forecasting accuracy, making them a promising alternative for real-world application. Additionally, SNNs excel in capturing temporal dependencies, effectively modeling complex dynamics in sequential data. This ability highlights their strength in handling intricate patterns over time. Finally, our study makes a valuable contribution to the field by presenting SNN as not only an energy efficient solution, but also a biologically plausible alternative for time series forecasting, paving the way for future advancements in neuromorphic computing. Thank you so much.